So now we are getting ready to look at acid-base titrations and pH curves. So the first kind of titration I want to do with you is a strong acid, strong base titration, and I'm going to take you through multiple steps along the course of a titration, and then we are going to graph it and look at a pH curve, and then talk about the pH curve for a strong acid, strong base titration. It may end up needing to be 2 videos. So if I can get my pen to come back, we'll go ahead and start. Okay, so what we're going to look at is a titration between 50 milliliters of 0.20 molar nitric acid and 0.100 molar sodium hydroxide. And the first thing we want to look at is where we have, let's do this at 1, no sodium hydroxide added. Okay, so if we have no sodium hydroxide added, all we have is this. So we have 50 milliliters of 0.20 molar nitric acid. Okay. Now you know that this, or by now you should know that this is a strong acid. So if that strong acid is put in water, because there's nothing else there, because I haven't added any sodium hydroxide left, you would have hydronium ion and nitrate ion. And I drew our arrow wrong here because I have equilibrium on the brain. So because this is a strong acid, this is all stoichiometry. I get all products. So really what that means is I don't have these around anymore. So if my molarity of nitric acid was 0.20 molar, that means my concentration of hydronium is 0.20 and my concentration of nitrate is 0.20. Now nitrate, because it is the conjugate base of a strong acid, has no acid-base properties in water. It's not going to contribute to pH at all. So all I have to do to calculate pH is to do the negative log of the hydronium ion concentration. So negative log of 0.20, and that gives us a pH of 0.6. I need to check sig figs. Okay, so I've got 2 sig figs here. Oh wait, we've been doing lots of 2 sig figs. Let's go ahead and give ourselves 1 more so that we can see something different. All right, so we have 3 sig figs, so I need 3 numbers after the decimal. So the pH of that solution is 0.699. And we need to remember what these are because we're going to graph them later. Really, all you could have done had been like, oh, strong acid, negative log of that concentration, which is essentially what I was doing here to get pH. I just wanted to explain why. Okay, second thing we're going to do, 10 milliliters of 0.100 molar sodium hydroxide added. Okay, you now have a reaction because you have the sodium hydroxide interacting with the nitric acid. And so what we want to do is we want to write balanced equation. So I have nitric acid and I have sodium hydroxide. When those two interact, we will get sodium nitrate and water. And here's our fence. And we are going to do, let's do initial change now. Think about this. If you have a strong acid and a strong base, these two are going to push the reaction to the right. So you are going to end up with these two products. You're not going to have some kind of equilibrium going on. And in strong titrations, you're going to do just like a limiting reactants table, an initial change final table. And because we have two different things reacting, we can't just use molarities. So on our initial line, we need to determine moles. So to do that, I need to look at how much acid do I have. And I'm going to introduce you to something here called millimoles. You don't have to use millimoles. You can. Makes the math a little bit easier, but if you hate it, then don't do it. In class, we'll show you the relationship between millimoles and molarity. I just don't want to do that on this video. Okay, so I've got 50 milliliters of nitric acid and it's 0.2 molar. So my milliliters will cancel. I am left with millimoles. 50 times 0.2 is going to give me 10. Now, I'm not going to worry about sig figs right now. I'm going to come back and do them later. So I have 10 millimoles. Then I want to calculate my sodium hydroxide. So here I've got 10 milliliters of sodium hydroxide, milliliters, millimoles, 0.1. So 10 times 0.1 is going to give me 1 millimole. Now, I'm not going to worry about water. I'm really not going to worry about this salt either, because honestly, if I were doing this as net ionic, your sodium and your nitrate would be spectator ions. So really, we're looking at the interaction between H plus and hydroxide. So I'm not concerning myself at all with what's going on over here. Okay, so now this ought to look like limiting reactants, and you'll be able to tell that hydroxide is limiting. So it will go down by 1. H plus will go down by 1. So I will have no hydroxide left, and we will have 9 millimoles of H plus left. Now, in order to calculate pH, I need to know the concentration of this. So I'm going to take millimoles divided by milliliters. Well, my total volume is going to be 50 and 10, which is 60. So if I do 9 divided by 60, whoops, I don't know how to use my calculator. 9 divided by 60, I get 0.15 molar. Now, if I check sig figs, I'm using 3 everywhere, so this is 0.150 molar. And then I want to know pH. So let me erase my scribbles over here to calculate pH. And pH is negative log of H plus. This is my H plus, negative log of 0.150. Is 3 numbers after the decimal, so 0.824. Okay, does that make sense? We'd add a little bit of base. Shouldn't our pH rise? Yes. Okay, so now we're going to continue. All right, so this is 3. All right, here we've got 20 milliliters of 0.1 molar sodium hydroxide is added. All right, so once again, we need to write our balanced equation. So we've got our nitric acid plus our sodium hydroxide is going to sodium nitrate, which we know is a spectator and we're not going to worry about, and water, and we're not going to worry about that either. I'm going to draw the fence just because we're used to that. And then I have initial, change, and final. All right. Now, if you think about the previous slide, our amount of nitric acid has not changed. So we don't need to recalculate this because we haven't changed that amount. So I'm just going to go ahead and add in 10 millimoles here. Okay, but our amount of sodium hydroxide has changed, so we're going to continually recalculate that. So I've got 20 milliliters, and I want to go from milliliters to millimoles, and I'm going to use molarity to do that. So 20 times 0.1 is going to give us, I'm going to go back to white, 2 millimoles. So once again, hydroxide is limiting, so our change, it'll go down by 2. I'll be left with no hydroxide and 8 millimoles of our acid. Total volume, I've added 20 milliliters of sodium hydroxide, and if we remember before, we had 50 milliliters of our acid, so this is 70 milliliters. So 8 divided by 70 gives us 0.114 molar. And then to get pH, I'm going to do negative log of this concentration. And that will give us 0.942. And that makes sense because we've added a little bit more base. Okay, I'm going to continue. I'm going to go ahead and I'm going to get rid of what we've done here. Our amount of acid has not changed, so I'm not changing that. So the next thing we're going to do is we're going to look at 50 milliliters of 0.10 molar sodium hydroxide. Okay, so I'm going to say 50 milliliters. I want to go from milliliters to millimoles because this is a chemical reaction and I've got to compare moles of each. So 50 times 0.1 gives us 5 millimoles. And we will go down by 5. So we'll have no hydroxide left. We'll have 5 millimoles of acid left. Our total volume is 50 and 50 is 100. So we're doing 5 divided by 100, which gives us 0.0500 if we want to worry about sig figs. So our pH here is going to be negative log of 0.0500. So negative log of that number is 1.30. I'm going to draw an arrow between these two because I've got to go back. We're going to graph this later, so I want to be sure that I've got all our values straight. Okay, next one we're going to do is we want to look at 100 milliliters of 0.1 molar sodium hydroxide. Okay, so acid has not changed. I'm going to leave that the same. Our base is different. So we need to get to moles. So milliliters times molarity. So 100 times 0.1 is going to give us 10 millimoles. All right. At this point, you should see that the moles of each of acid and base are equal. So when the moles of acid and base are equal, we have reached this special situation that is called the equivalence point. And if you remember from your vocabulary words, the equivalence point is when the moles of H plus or acid are equal to the moles of OH minus or base. So what will happen is if both of these are going down by 10, we have neither left. Now, what that means is all we have left is the salt and water. So the salt, because the nitrate ion is the conjugate base of a strong acid, that has no acid-base properties in water. Alkali metal, cations have no acid-base properties in water. So the only thing that's going to contribute to pH is the H plus concentration that is contributed by water. So at this point, I'm going to go back to pink. because we are at the equivalence point of a strong acid, strong base titration, our pH is 7, because we're doing negative log of 1 times 10 to the negative 7th. Okay, so let's continue. Let's say we're doing this in lab, and we are overrunning our endpoint, which is quite common. So what we're going to do here is, let's go to a different color. Let's go to this color up here. So we now have 150 milliliters of 0.1 molar sodium hydroxide added. Okay, so same thing, amount of nitric acid has not changed, but now we're going to take milliliters times molarity, and when we do this, we're going to get 15 millimoles. So at this point, our hydroxide is in excess, and our acid is limiting. So our change here is going to go down by 10. We've run out of acid, but we have 5 millimoles of base left. So if I take, go away, if I take my total volume, which is 200, so I've got 5 divided by 200 is 0.025 molar, and then I need the pH of that. Now, that's hydroxide, so I can't do pH. What I need to do here is I need to actually calculate hydroxide ion concentration, or I need to find POH and then go to pH from there. So let's do POH first. So POH is going to equal negative log of hydroxide ion concentration. So negative log of that number gives us 1.60. So pH is going to be 14 minus 1.60, which will give us 12.40. But we need, I screwed up on these other two. I should have had 3 numbers past the decimal. Let me finish this one first. So I have 12.398. Okay, let me see if I can squeeze it in there. 12 point, come back, 398 is our pH, which would make sense because we have excess base. All right, let's go even further and see what would happen. So I'm going to take all of this out of here. And let me go to the next slide. So this will be 7. Let's do 200 milliliters of 0.1 molar sodium hydroxide. Okay. So now we have 200 milliliters. We're taking milliliters times millimoles. This is like we walked away from our titration totally, which you wouldn't do, of course. But let's say we did. So now we have 20 millimoles of hydroxide. Both of these will go down by 10 because that's the smaller amount. No acid is left. We have 10 millimoles of base left, and our total volume is 250 milliliters. So 10 divided by 250 gives us 0.0400 molar hydroxide. I'm completely out of room, so I'm going to go over to the other page to do that. 0.0400 molars hydroxide ions. Okay, so now what we want to do with this, I'm just going to calculate it a different way. To get hydroxide ion concentration, I want to take Kw divided by, to get hydronium or ion concentration or H plus concentration, I'm going to take Kw divided by hydroxide ion concentration. and I get 2.5 times 10 to the negative 13th molar. I know I'm not doing sig figs. There we go. And to get pH, I'm going to do negative log of this value, 2.5 times 10 to the negative 13th. So I will get 12 point, everything that I've been using has had 3 sig figs, so I want to go 3 digits past the decimal, 12.602. Let's stop. I'll do another video because this one's pretty long, looking at the titration curve of a strong titration.